To understand why Webb is causing so much disruption, you have to understand what it can actually see that no other instrument could. Older telescopes, including the legendary Hubble Space Telescope, primarily observe invisible and ultraviolet light. But as light from extremely distant galaxies travels across billions of years and the universe expands beneath it, that light gets stretched, its wavelength lengthens, shifting from visible light into the infrared. Astronomers call this redshift, and the more distant and ancient the object, the more extreme the shift becomes. Hubble could catch glimpses of this shifted light, but only faintly, at the very edge of its capability. Webb was purpose-built to solve that problem. Its massive gold-coated mirror, over 21 feet across, and its suite of infrared instruments allow it to detect light that has been traveling toward us for over 13 billion years. Light stretched so far into the infrared that it was effectively invisible to every previous generation of telescope. In practice, this means Webb can photograph galaxies as they appeared just a few 100 million years after the Big Bang, a window into the universe that had simply never been opened before. And when that window opened, astronomers expected to see exactly what the models predicted: small, faint, irregular blobs of gas and young stars. The messy beginnings of galaxy formation. Instead, in survey after survey, including the landmark JADE survey, short for the JWST Advanced Deep Extragalactic Survey, Webb found galaxies that were bright, massive, and in some cases already showing organized structure, at a point in cosmic history when they should have barely begun to form. Was it a calibration error? An instrument fluke? That was the first assumption. But what if you think it's a mistake, and then it happens again? And again? The evidence has only mounted since Webb's first images were released in the summer of 2022. Among the most striking cases is a galaxy catalogued as GNZ11, first flagged by Hubble but confirmed and studied in far greater detail by Webb. Its light left its source when the universe was roughly 400 million years old, barely 3% of its current age. And yet GNZ11 is unexpectedly luminous, unexpectedly massive, and shows signs of vigorous, rapid star formation that current models struggle to explain in such a short window of cosmic time. Then came a wave of even more extreme candidates identified through the JADE survey, galaxies so distant their light suggests they existed within the universe's first 300 to 400 million years. Several of them appear far too massive for their age. One analysis, drawing on early Webb data, suggested that some of these galaxies contain stellar masses that current models of star formation simply cannot produce that quickly, no matter how efficiently gas collapses into stars. Astronomers have taken to calling this, half jokingly and half seriously, the universe-breaking problem. Because if these mass estimates hold up under further scrutiny, one of two things has to be true. Either galaxies formed far faster and more efficiently in the early universe than any model currently allows, or our understanding of the timeline itself needs to be rebuilt from the ground up. It's worth pausing here, because this is where careful science matters most. Not every headline-grabbing, impossible galaxy survives peer review. Some early mass estimates have already been revised downward once follow-up spectroscopy, a more precise way of measuring distance and composition, was completed. Science self-corrects, and several of the most extreme early claims have since been tempered by better data. But even after that correction, even after the most sensational cases were walked back, a real and stubborn tension remains. Too many of these early galaxies are still bigger, brighter, and more structured than the standard model predicts. Not impossible. Not violating the laws of physics. But uncomfortable. Sitting right at the edge of what our theories can explain, and in some cases, past that edge entirely. What do you think it means when the universe keeps returning answers the equations didn't expect? Faced with this tension, the scientific community hasn't panicked, but it has split into camps, each proposing a different way to patch the model. The first and most conservative camp argues that galaxy formation was simply more efficient in the early universe than we assumed. In this view, primordial gas clouds, denser and less obstructed by competing structures, could collapse into stars far more quickly and completely than the same process happens today. Under this theory, nothing is truly broken. We just underestimated how good the early universe was at building things fast. Faced with this tension, the scientific community hasn't panicked, but it has split into camps, each proposing a different way to patch the model. The first and most conservative camp argues that galaxy formation was simply more efficient in the early universe than we assumed. In this view, primordial gas clouds, denser and less obstructed by competing structures, could collapse into stars far more quickly and completely than the same process happens today. Under this theory, nothing is truly broken. We just underestimated how good the early universe was at building things fast. A second camp points towards supermassive black holes. Some Webb observations have revealed black holes at the centers of early galaxies that appear disproportionately massive compared to their host galaxy, the opposite of what we typically see in the modern universe. One provocative idea suggests these black holes may have formed first, directly from collapsing gas clouds rather than from dying stars, and then rapidly seeded the growth of the galaxies around them, accelerating structure formation far beyond the old timeline. A third, more radical camp has started asking an even bigger question. Does this mean our expansion history itself needs revision? A small but vocal group of cosmologists has proposed modifications to the standard model, adjustments to how we calculate cosmic distances and timelines, or alternative frameworks entirely, that could shift when these galaxies actually formed relative to the Big Bang, potentially easing the tension. None of these theories has been proven. All of them are being tested, right now, against new Webb data as it streams in. And that uncertainty is not a weakness of science, it's the process working exactly as it should. But it does mean that, for the first time in a generation, our timeline for the birth of the universe is genuinely, openly up for debate. But here's the question scientists still can't answer. If the early universe really did build galaxies this fast, what does that say about how common, or how inevitable, structures like our own galaxy, our own solar system, even life itself, might be? Beyond the mainstream debate, Webb has also captured a handful of images that, while fully explainable by known physics, are strange enough to have earned their own reputation among astronomers. One of the most photographed is an object informally nicknamed for its almost impossibly symmetrical appearance, a foreground galaxy positioned so precisely in front of a background galaxy that its gravity bends the distant light into a nearly complete ring, a phenomenon called an Einstein ring. Gravitational lensing itself is not exotic. Einstein predicted it over a century ago, and telescopes have photographed distorted, arc-shaped lenses for decades. What makes certain Webb-captured rings remarkable is simply their precision. The alignment required to produce a nearly unbroken circle is extraordinarily rare, a matter of pure cosmic coincidence occurring across a canvas of billions of light years. Rare does not mean impossible, and it certainly doesn't mean designed. But it's a useful reminder of just how much can happen by chance alone in a universe this large, and how easily coincidence can look, to the human eye, like intention. Webb has also detected unusually large exoplanets orbiting surprisingly young stars, at distances that challenge our standard models of how planets form from the disks of gas and dust surrounding new stars. One such world, roughly 7 times the mass of Jupiter, orbits its star at a distance far greater than where our own models say a planet of that size should be able to form, around a star only a few million years old, barely enough time, in theory, for a planet like that to come together at all. The leading explanations are not exotic. Some planets may form through a faster process called gravitational disk instability, where a large, unstable region of a protoplanetary disk collapses directly into a planet rather than slowly accreting like a snowball, as our own gas giants did. Others may have formed closer to their star and migrated outward over time. Neither explanation requires anything beyond established physics, but both stretch the edges of what we thought we understood about how solar systems come together, and how quickly. It's tempting, when you line these anomalies up side by side, the 2 early galaxies, the 2 large planets, the 2 perfect rings, to feel as though you're looking at a pattern. And maybe you are. But the honest answer is that the universe is large enough and old enough that genuine statistical rarities are guaranteed to exist somewhere in it. Our job, and Webb's job, is to keep looking closely enough to tell the difference between a coincidence and a clue. Would you have believed any of this was possible before seeing the data yourself? Which brings us to the tension that no camp has fully resolved. Set aside the individual anomalies for a moment, the odd planet, the strange ring, even the occasional discredited, impossible galaxy that didn't survive peer review. What remains, even in the most careful, most conservative reading of the data, is this: a meaningful number of galaxies existed earlier, and grew faster, than the standard cosmological model predicts. Not by a small margin, comfortably absorbed by measurement error. By a margin significant enough that multiple independent research teams, using different instruments and different analysis methods, keep arriving at